specific. Level roar. That's not a CFM LEAP engine anymore. That's something China built from scratch, and it just crossed 5,000 flight hours. For the last decade, every time China showed off its homegrown commercial jet, the COMAC C919, there was an asterisk. A quiet one. A polite one. Nobody said it out loud in the press releases, but every aviation analyst knew exactly where to look the engines. The C919 flew on CFM LEAP-1C engines. That's a joint venture between America's GE and France's Safran. Beautiful piece of engineering. Also completely outside China's control. One export restriction, one sanctions escalation, one bad diplomatic quarter, and China's entire commercial aviation program is grounded.
What you see here is merely the surface. The true innovation lies in the engine mounts.
Literally, that was the choke point. Not the airframe, not the avionics, the engine. But here's what nobody is talking about properly. The CJ-1000A, China's indigenous engine, just cleared 5,000 flight hours on a C919 test bed. And by the time this video ends, you're going to understand why that number doesn't just represent a milestone. It represents the moment the last lock on China's aviation independence was broken. And more than that, you're going to understand why this engine isn't a copy of Western technology. In two specific, measurable ways, it may have leapfrogged it. Let's get into it. First, a quick explainer because this matters. When people say jet engine, most people picture something like a blowtorch strapped to a wing. Raw heat, raw thrust. That's actually not how modern commercial aviation works. Modern commercial jets use what's called a high bypass turbofan. And the key word is bypass. In this design, a massive front fan, we're talking nearly 6 feet in diameter, pulls in an enormous volume of air. But only a fraction of that air goes through the hot combustion core. The majority of it bypasses the core entirely and flows around the outside of the engine as a cold stream. The ratio of that cold air to the hot core air. That's the bypass ratio, and it's one of the most important numbers in commercial aviation. Here's why. A higher bypass ratio means more of your thrust comes from that cold air moving fast, which is far more fuel efficient than pure combustion thrust. The CFM LEAP-1C, which the C919 currently uses, has a bypass ratio of roughly 11 to 1. That's state of the art. That's why modern aircraft burn 15% less fuel than the generation before them. The CJ-1000A, it's targeting a bypass ratio between 10 to 1 and 12 to 1, right in the same ballpark. On a first-generation indigenous design, that's the number that silenced a lot of skeptics when it came out. Because bypass ratio isn't something you can fake. You can't fudge it in a press release. It shows up directly in fuel burn. It shows up in operating costs. Airlines will measure it against their own data, and they'll know within months whether China is telling the truth. But bypass ratio is only part of the story. And honestly, it's not even the most interesting part. The most interesting part is what's happening inside the engine. In a place so hot, it shouldn't exist. Here's a fact that sounds like science fiction. The hottest section of a modern turbofan engine, the high-pressure turbine, operates at temperatures that exceed the melting point of the metal it's made from. Read that again. The turbine blades are operating in gases hotter than the temperature at which the blade material would normally melt. They should not exist, and yet they do, because of two innovations that took the West decades to perfect, and that China has now, by all credible engineering assessments, achieved independently. The first is single crystal superalloys. A normal metal, at the microscopic level, is made of many small crystals packed together. At extreme heat, those grain boundaries are weak points, stress concentrators. The metal creeps, warps, eventually fails. Single crystal superalloys eliminate that problem entirely. The blade is grown as one continuous crystal. There are no grain boundaries. The result is a material that maintains structural integrity at temperatures that would destroy conventional metals. The West cracked this in the 1960s and 70s. It's been a core Western advantage ever since, and one of the hardest things to reverse engineer because the manufacturing process is extraordinarily sensitive. You're essentially controlling the solidification of molten metal at the atomic level. China's AECC, the Aero Engine Corporation of China, has reportedly achieved this for the CJ-1000A's high-pressure turbine. Independent confirmation is still limited, but the flight hour data is hard to fake. If those blades were failing, the engine wouldn't be clearing 5,000 hours. The second innovation is Ceramic Matrix Composites, CMCs. This is where it gets genuinely exciting, and where most YouTube coverage completely whiffs the story. CMCs are materials where ceramic fibers are embedded in a ceramic matrix. The result is something that weighs roughly 1/3 of a comparable metal component, but can withstand temperatures exceeding 500 degrees Celsius. In a turbofan, that means you can shrink or potentially eliminate some of the elaborate air cooling systems that bleed efficiency from the engine. GE Aviation pioneered CMC use in the LEAP engine. It was one of their signature breakthroughs. China has been aggressively pursuing CMC capability since at least 2018. And here's the piece that changes the calculus entirely. In 2025 and into 2026, Chinese aerospace research institutions began publishing results from AI-driven computational fluid dynamics applied to turbine blade design. This isn't theoretical. Multiple peer-reviewed papers, cross-referenced by Western aerospace analysts, describe using large-scale simulation models to optimize the internal cooling architecture of turbine blades. The tiny, precisely shaped holes that channel cooling air through the blade. Those cooling holes are handcrafted knowledge in the West. Thousands of engineer hours, decades of iteration. China is using AI to compress that timeline. That is not catching up. That is a different path to the same destination, and potentially a faster one for future iterations. Now let's talk about what this actually means for the global aviation industry, because the numbers here are staggering, and they haven't been properly contextualized anywhere. China is the fastest growing aviation market on the planet. COMAC has a backlog of over 200 C919 orders, almost entirely from Chinese domestic carriers. Right now, every one of those aircraft that comes off the production line with a LEAP-1C engine represents roughly $214 million in engine revenue for GE and Safran. Run that math on a Fun's 200 aircraft with 2 engines each. That's somewhere in the range of 28 to 133 billion in engine revenue over the delivery lifecycle of that backlog alone. Not counting maintenance, not counting spare parts, not counting future orders as Chinese carriers expand. Every aircraft that leaves the COMAC factory with a CJ-1000A instead of a LEAP-1C is a direct subtraction from that number. Now, China isn't going cold turkey overnight. Certification takes time, fleet transitions take time, but the direction of travel is unmistakable. In 2026, COMAC confirmed it is moving toward a 100% domestic propulsion supply chain. The term Chinese officials are using, quietly but consistently, is autarky, self-sufficiency, no external dependencies. The economic logic is obvious. Why pay $14 million per engine to a geopolitical competitor when you can build it yourself? But there's a second layer here that's less obvious. Western engine dominance wasn't just about the hardware. It was about the data. The CFM56, the predecessor to the LEAP, has accumulated hundreds of millions of flight hours across the global fleet. That data feeds maintenance schedules, failure prediction, safety certification frameworks. An airline's insurer wants to know how many times that engine has flown before they'll price your policy. The CJ-1000A has 5,000 hours. The LEAP-1C has billions. That reliability gap, that trust gap, is real. And it's going to determine whether the CJ-1000A stays a domestic Chinese engine, or whether it eventually appears under the wings of aircraft in Southeast Asia, the Middle East, or Africa. That's the next frontier. And the signal to watch, the actual bellwether, is AECC certification, the European Union Aviation Safety Agency. If China pursues and achieves AECC certification for the CJ-1000A, that's the moment this engine becomes a global story, not just a domestic one. They haven't applied yet, but watch late 2026. Watch carefully. So, is Western aviation dominance actually over? Here's my honest read. In terms of technology parity, for for a narrow-body commercial engine in the 25,000 to 35,000 pound thrust class. China has, with the CJ-1000A, effectively closed the gap, not in every dimension, not with 50 years of operational data, but in terms of what comes out of the nozzle and what the thermodynamic numbers say. Yes, parity, on the current evidence, is real. In terms of market dominance, Western manufacturers will maintain their global position for at least another decade. Airbus and Boeing aren't being displaced. Existing fleets don't get swapped overnight. And outside China, no major airline is going to gamble a 200 million aircraft on an engine with 5,000 flight hours when a proven alternative exists. But here's the question that actually matters, and almost nobody is asking it: what happens in 2030? By 2030, the CJ-1000A will have accumulated tens of thousands of flight hours. By 2032, possibly hundreds of thousands. The trust gap shrinks with every uneventful landing, and China will be pitching this engine aggressively, with favorable financing from state-backed banks to every developing nation that can't afford to be caught in a Western supply chain dispute. That's the real competition, not, can China's engine match GE's engine today? The question is, who controls the propulsion supply chain of the global South fleet in 2035? That is an open question. And it is the most consequential open question in commercial aviation right now. Here's what I want you to take away from this. The CJ-1000A story isn't really about one engine. It's about what happens when a nation decides that a technology choke point is unacceptable and throws a decade of focused, state-backed AI-assisted engineering at closing it. The material science, the single crystal superalloys, the ceramic matrix composites, the AI-optimized cooling architecture. That is the real story. That's what makes this engine more than a symbolic achievement. That's what makes it a foundation for everything that comes next. Watch the AECC certification application. Watch the flight hour accumulation rate. Watch which Southeast Asian airlines get the first pitch deck from COMAC's sales team. And if you want to understand the engine that set all of this in motion, the CFM LEAP-1C, and exactly how it became China's dependency in the first place, that breakdown is in the next video. Link is in the description. Subscribe if you want the geopolitics and the engineering together, because the most important stories right now are sitting exactly at that intersection. I'll see you soon. Take care.